No, just a practical announcement. So remember that tonight we have a social dinner at the High Allied restaurant, which is walking distance from here. The social dinner is at 9 p.m. You can find the address in the whiteboard, which is at the registration desk, or otherwise in the web page. Okay, and some of us will leave from the main door of the Residencia de Estudiantes at 8:40 p.m. Okay, in case you want to come with us.
Okay, good morning to everybody. It is my pleasure to introduce you the first speaker of this morning session. And the first speaker is my colleague and friend Alberto Ibort from the University Charles III, and also is a member of our Institute of Mathematical Sciences, IMAT. And the title of the talk of Alberto is the groupoidal picture of quantum mechanics and the classical and semiclassical limits. Please, Alberto.
Okay, so thank you very much. It's been a pleasure to be here, and I will try to say a few words about this new picture of quantum mechanics, which is, oops, sorry. My God, let me get used to that. Okay. So what I'm going to talk is about a new picture of quantum mechanics that has been emerging from the ideas and reflections inspired by the developments of physics and mathematics in the 20th century. I'm going to present in a rather sketchy way, just to try to transmit the basic ingredients of this proposal, of this picture. And for that, I will begin by observing that in the physics of the 20th century has been deeply influenced by the puzzle of quantum mechanics. Not only physics, but mathematics too. Actually, it was von Neumann's formalism of Hilbert spaces and linear operators that provide the new geometry that was adequate to describe the foundational ideas of quantum mechanics. But the success of the formalism was so strong that it, so to speak, blurred part of the conceptual basic ingredients that led to the development of quantum mechanics at first. And one of these main ideas, original ones, that probably has been perceived in a sort of deformed way was the contribution by Heisenberg about the notion of transitions, being the transitions that we observe for quantum systems, the basic ingredients of the theory. We have been having, I myself, the impression that kind of mathematical ignorance that Heisenberg was discovering matrix mechanics and was discovering the algebra of matrices. But it was much more than that, because what he was doing was to realize that matrices, that is nothing but the natural algebra of a groupoid, were the basic mathematical object that you have to use to describe transitions. This diagram was kind of the puzzles that, for instance, Heisenberg was facing, the transitions observed in a sodium atom between different energy levels. And actually it was Alain Kohn, much later, that was, that realized that the composition, the basic composition principle for transitions, what is called the Ritz-Fichter law, is nothing but the composition law of the groupoid of pairs of a finite number of outputs. Much before Alain Kohn was Julian SCHWINGER, that when he was trying to abstract, to put framework, conceptual framework for the development of the theory of interaction between electromagnetism and matter, because of what he was awarded the Nobel Prize. He introduced an abstract setting that was trying to convey that the fact that the laws of atomic physics had to be expressed in a symbolic language. And that symbolic language, he was presenting it, introducing a notion. There was the notion of what he called selective measurements. And if you look at the writings by himself in the mid-50s and the early 60s, he wrote exactly that the composition of these symbols representing transitions of quantum systems, they satisfy the axioms of a groupoid. Actually, he was using the algebra of the groupoid instead, but it's already there. So this is the departing point we are taking, and is that the description of a quantum system, physical system in its entirety, this means including not only the observed outputs, but the transitions that this system experiences, is captured very nicely, very naturally by the notion of groupoids. So let me move, following this, to establishing the basic, so to speak, axioms, or if you want, principles inspired by elementary physics notions, that the outputs of, when we observe a system, there will be two kinds of elements. One will be the outputs of the observable quantities that we will be interested in, and this will be elements A, B, X, Y, whatever, in a set, omega. There will be also the transitions that are observed between the different outputs provided by the observation of the system. These transitions will be described using this sort of categorical notation. So alpha, beta will be transitions such that the source of the transition will be the outcome A, the target of the transition will be the outcome B. For instance, think about energy levels, or the different firings of detectors when you are observing what happens in storage rings or accelerator rings, for instance, right? So there's going to be a couple of maps from the set of all transitions, gamma, of the system, which is the source and the target maps, defined in the obvious way. And these transitions can be composed. Actually, nature composes them for us. This means that there is a composition law in the space of composable pairs, alpha and beta, that are composable if the source of the second transition is the target of the first one. And this composition law, that in actual experiments simply means observing one transition after another one, is going to be another transition, and it satisfies an obvious natural mathematical axioms. On one side, it's associative. Whenever three transitions can be composed, there are units, transitions that essentially means doing nothing to the system. And the most important one from a conceptual point of view, which is the existence of the inverse of any transition. This axiom is nothing but what Richard Feynman called the principle of reversible microscopic reversibility of quantum systems, which was stated clearly and precisely in his PhD thesis in 1948. But we know that these are just the axioms of a groupoid. So, in this sense, groupoids provide a kinematical setting to describe what we do when we observe systems, including not only the outputs of measurable quantities, but the transitions that the system experiences. These transitions, you may think, is the sort of idealization of what in the old times of quantum mechanics were called quantum jumps, right? Some simple examples just to warm out is, for instance, in the case of discrete output systems, the simplest possible one is the abstract qubit, that will be a system that we'll have two outputs, call them plus, minus, 0, 1, whatever, black and white, whatever. And there will be two transitions, a transition from plus to minus and the transition from minus to plus, the inverse one, together with the corresponding units, or in a more schematic or synthetic way, this A2 diagram. If we have, you can generalize that very easily and think of any system with a finite or countable number of outputs, and on them, a system describing semi-bounded, the groupoid describing semi-bounded systems, like the harmonic oscillator, for instance, could be described by the groupoid whose inputs are going to, whose outputs are going to be the integer numbers, or the natural numbers, 0, n, 1, 0, n, 2, 1, n, etc. And the corresponding transitions among all these outputs that will be generated by transitions alpha n from n to n plus 1, and the inverse of that from n plus 1 to n, and all the possible compositions. Of course, this is very simple, very schematic, and you would like to include also in the picture. Sorry, yeah.
Is there any example in nature of inverse transition?
Sorry?
Is there any example in nature of inverse transition? What is an inverse transition?
What is an
Inverse transition.
the inverse?
Yeah.
No, in nature.
In nature, like an actual
The real world.
quantum process which has a transition and then an inverse transition.
Oh yes, of course. I mean, whenever you can think, for instance, in the case of the situation where you are describing the excitations of the level of energy levels in atoms, right? So you can excite an atom, and then you can observe the transition of the ground, so to speak, state to one excited state, right? Absorbing an external photon, if you wish. This will be the source of the transition, right? And then this transition goes down, and the atom sites themselves emitting again a photon, and goes from this excited level to the ground one, right? So for all transitions in the, when you look at the, for instance, the spectrography data of atoms, for all transitions there are the corresponding inverses that corresponds to the excitation of the atoms, right? Not only that, for instance, you may play the following, actually this is an experiment that has been done. You can have a particle moving in a ring, you may think of an accelerator ring. Now accelerators are very big. In the past, in the 20s, they were very small. They were like that, right? And Lawrence, for instance, were building accelerators this size, right? And then you put detectors in various places, and then you can tick. You can simply keep the control of the different firing of the detectors when the particle is moving inside the accelerator. And then, for instance, you can use 3 detectors situated in the vertices of a triangle, A, B, and C, and then you will see transitions. That means the firing of the detector A, and after that B, and then you will also see the firing of the detector B, and after that A, right? So this intrinsic reversibility of transitions is an important and significant action of the theory. Another question, but we come back to that later, is, well, now suppose that you want to construct out of these ingredients some interpretation of, for instance, realistic interactions between matter and electromagnetic fields. So eventually you are leading to a quantum field theory. Then you would like to introduce causality into the picture. So how do you break this intrinsic symmetry and construct a causal picture of everything? This is a different, well, this is another problem which comes later on, right? What I would like to say now is that you would like to also incorporate into the picture the statistical interpretation. For that, we can just follow the principle established by Chenkov in his fundamental description of statistics, and is that the job, in this case in our case will be the theoretical physicist, is to construct a mathematical model of the random phenomena observed when studying a physical system. we have been since the beginning of the 20th century, we have such a model with us, and it's provided by what I like to call Kolmogorov of spaces, probability spaces. This means omega is a set, B is a sigma algebra, and P is a probability measure or probability distribution. We have been this model has been, again, so successful that it permeates every branch of mathematics today, right? But what happens if you want to incorporate not only you want to take into account not only the outputs, the observed quantities, but also the transitions. You have to extend this probability model. How do you do that? Well, one way to do that, well, actually, it's been the work of a remarkable number of people along a number of decades to do that. And just let me put together some of the main contributions to this idea, starting with Mackie, Han, Alencon, Jean Renaud, and many others that have led to the notion of what we call, or we can be called today, measured groupoids. What is that? Well, of course, apart from having a Kolmogorov space in the space of outcomes, it means a probability measure there, you will need something also to take into account the statistics of the observed transitions. The beautiful idea behind that, just to make a long history short, is to consider that you have what Alencon calls a transverse function. This means a function that assigns to elements in the probability space omega A measures which are supported in the inverse images of the target map or the source map, depends how do you want to play that, and which are consistent with the transformation, the action of the groupoid on itself. So gamma here is the groupoid, this is the source, this is the target, this is the map. L alpha means composition on the left by element alpha in the groupoid, so it's mapping, this map is mapping the inverse image of T corresponding to A into the inverse image of B corresponding to B. And then we will require that this transverse function is consistent with the inner symmetry of the groupoid by leaving these measures, transforming these measures among themselves. This is what in the language which is favored by people, by C-star algebraists, is what is called a system of left invariant hard measures, and it provides the basic ground to construct a statistical interpretation of the groupoid, because all these measures can be put together, can be integrated along the measure on the space of units, and what we will have at the end is the groupoid, the algebraic groupoid, together with the class of the measure that has the structure. It disintegrates in this form along the fibers of the target or the source map to provide the basic statistical interpretation of a groupoid. So, for instance, the simplest and the most conspicuous example is the von Neumann's group measure construction, where now what we will have is a group, by the way, is a groupoid, for instance, locally compact, so we have a hard measure on the group. The group acts on the probability space omega and acts in a measurable way, and leaving the probability measure quasi-invariant. This has associated in a natural way a groupoid that sometimes we call it the action groupoid, which is just, as I said, the Cartesian product of G with omega, and the obvious, sorry, this is a comma there, the obvious composition map, and the and as a groupoid with the natural data, which is the probability space on the space of units, and the hard measure on the group is a measure groupoid. Another, just to end this part, another family of examples is provided by what I like to call kinematical groupoids. What is this? Well, in this case, what we will be working with is first space-time. We will have the the experimental devices provided in the most simple conceptualization by rulers and clocks, and these elementary measuring devices, we will have a space-time where we will locate, we will identify the events that we will be detecting and associated, and this space-time will carry some metric. Generally, we will think a Lorentzian metric, so this means a metric of signature, for instance, minus, plus, whatever. For instance, Minkowski space-time, if you wish. Then associated to this space-time, there are, well, various natural groupoids. The first one is what I like to call the Riemann groupoid that consists of all isometries. Here we can use the tangent spaces or the cotangent spaces on isometries between the tangent space at the point X to the tangent space at the point Y, or we can also use the cotangent bundle, the cotangent spaces if you wish. So with the obvious source and target maps and the obvious compositions, this is a Lie groupoid actually. But even better than that is what I like to call the Poincaré's groupoid of space-time, where now the space of outcomes, the space of objects of the groupoid, is the cotangent bundle of the space-time itself. Here it is, the cotangent bundle. And now the elements of the groupoid are triples, where we have covectors, px, isometries, txy, and the image of the covector py with respect to the isometry txy star, right? So there is, again, an obvious composition law here, and this is, again, a groupoid whose, well, the transitions leaving a point invariant, they form a group, and they are called the isotropy groups of the groupoid, as you know. And in these cases, in these two cases, the isotropy groups of these groupoids are nothing but the Lorentz group, the group of Lorentz transformations at the tangent bundle or the tangent space or the cotangent space of the given point of our space-time. One of the consequences of having kinematical groupoids is that you can ask questions like the one that was asked and solved by Eugene Wigner himself when he introduced the notion of, or when you want to talk about elementary particles. What is an elementary particle? Well, according to, well, it was Wigner, as I'm saying, that he introduced the notion of elementary particle, identifying them with elementary quantum systems, meaning by that unitary, reducible unitary representations of Poincaré's group. This was Wigner's idea. Of course, if you have a generic space-time, the group of isometries, global isometries, the diffeomorphisms preserving the metric, is trivial, right? Then there are no Poincaré group as such associated to a given space-time that will not be trivial. They will be generic, right? Yes, a generic perturbation of, for instance, Minkowski space-time. However, the notion of elementary particle is there. I mean, we have electrons. We have, independently if our space-time is curved, which is, right? And then the global Poincaré symmetry is only an approximation, right? It's only an idealization, right? But, of course, what you can do is simply exchange the notion of elementary particle or elementary quantum system by now considering irreducible unitary representations of Poincaré's groupoid, right? The beautiful thing is that you can compute them rather nicely by the corresponding extensions of Mackey's imprimitivity theorem that reflects nothing else by the Morita equivalence between the groupoid we are working with the isotropy groups of the groupoid. Actually, to be precise, the right identification is between the irreducible unitary representations of Poincaré's groupoid and irreducible unitary representations of the Lorentz group, which is the isotropy group, along the orbits of Poincaré's groupoid, which are given by an expression of this form, which is exactly the kind of expression that identifies the mass as one of the quantities in fixing the representations. I'm not going to talk much in these directions. I'm going to continue in a different, because I want to provide another fundamental ingredient to talk about all these things, and is to move into analyzing the algebra of observables of the system from this groupoidal perspective. Maybe later on, provided that I have some time, I will tell a little bit more about representations of groupoids. So, we would like to complete, so far everything has been kinematical, so I want to put some analytical flesh into the picture, and for that, I will need to determine, to say what are going to constitute the algebras of observables of my system. So, again, following von Neumann, the algebra of observables of a quantum system is going to be given by a von Neumann algebra, what we call today a von Neumann algebra, which is nothing but a subalgebra of the algebra of operators, of bounded operators on a Hilbert space H, complex separable Hilbert space, which is self-adjoint and which is closed under the weak or the strong operator topology, which amounts to say that this subalgebra of operators is closed under the double commutant, or coincides with the double commutant, which is the algebraic characterization of such property. This is the standard model or this is the model that von Neumann provides us to think about observables of quantum systems. Of course, now the question is, if I have a measured groupoid, do I have, in a natural way, an algebra of observables? And the answer is yes. Actually, there is a there is a natural construction of the algebra of a measured groupoid. I'm going to just sketch it for you to avoid to spend time in technical details, in the case that the groupoid is discrete countable, in which case the way to construct, one of the possible ways to construct the algebra of observables is to consider the left regular representation of the groupoid on itself. This one. This means that we assign to any function on the groupoid, with finite support, an operator on the space of the square integrable functions on the groupoid itself, which is simply the translated function by the action of alpha minus 1 on the left for any alpha, an element in the groupoid. So the closure of these operators corresponding to the left action of the groupoid on itself on the space of square integrable functions on itself is the von Neumann algebra of the groupoid. Of course, this is a slightly abstract picture, but we can make it much more specific, concrete, easy to use by introducing the convolution algebra of the groupoid, which is the natural extension of the notion of the convolution algebra of a group. Now we can define for any two functions of compact support the star product, the convolution product of these two functions, as simply using the standard formula for convolution. And then a function f is represented as an operator on the space of square integrable functions on the groupoid itself by simply convoluting with it, convoluting psi with f. Well, if the action of the group on the groupoid, on the space of units doesn't live invariant the measure, the probability measure P we have there has to be some square root factors, but I'm assuming that the action, the groupoid is what is called unimodular, and I'm avoiding spurious, factors that I will have to put in the general case. So for instance, just to make these abstract things concrete, what are the algebras of some of the examples we were commenting before? Well, in the particular instance of the qubit, the algebra of the groupoid is just the algebra of matrices, 2 by 2 matrices, is what is called a factor of type 1, 2. In this particular case, a factor is a von Neumann algebra whose center is trivial, consists only of multiples of the identity, Any von Neumann algebra is unital, has the unit element in there. The harmonic oscillator has an algebra which is just the algebra of bounded operators on L2, and is a factor of type 1 infinity. In the case of action groupoid, what we get is the construction that von Neumann himself introduced together with Murray in the famous series of papers, and it's what is called the cross-product algebra of the group G with the abelian von Neumann algebra of essentially bounded functions on omega. And this is an extremely rich source of examples, and the classification of factors, something that was achieved and completed by Alain Kohn in the mid-80s, was done starting or developing all these ideas, and has been a major driving force in the history, in the mathematics of the 20th century. This allows us this identification between quantum systems, groupoids, and the measured groupoids and their algebras to talk about the type of a quantum system as being the type of the algebra of observables of the corresponding groupoid. Just to finish this part, this general description of ingredients, let me say what now is a state. State, physical state, which is exactly the same as a mathematical state, is nothing but a positive normalized linear functional on the algebra of observables of the system. So it's a map from the algebra, the von Neumann algebra of the groupoid into the complex numbers, which is definite non-negative, so it's positive, and it's normalized. Of course, whenever you have a state, there is a natural representation associated to it, which is called the GNS representation, or Gelfand-Naimark-Segal representation. Such representation has a support space, which is a Hilbert space, which is nothing but the quotient of the algebra itself by what is called the Gelfand ideal of the state, which are all elements in the algebra such that rho of A star A is 0. So these null elements with respect to the state. The representation is constructed just by simple multiplication. And if the representation is non-degenerate, this means that there are no elements that are represented by non-zero, non-trivial element represented by 0, it is well known that there is associated to any non-degenerate representation of a positive definite function on the groupoid. On the group, in the case of groups, where this theory was originally developed, and in the case of groupoids, it extends naturally, where a positive definite function is just a function that when it's evaluated on the composition of pairs of composable elements in the groupoid, you will have matrices which are non-negative. Then there is a correspondence between non-degenerate representations, states. Well, there is a natural correspondence between states, non-degenerate representations, and positive definite functions on the groupoid. We can analyze states by looking at positive definite functions on the groupoid, on the quantum system. We are working it in a much, so to speak, direct approach and less abstract than considering the algebras themselves. Okay, let me say a couple of words now in order to end up with this part of the talk, this block, about classical systems. There has been a lot of ongoing debate since the origin of the old times of quantum mechanics about the quantum to classical transition. What it means to be classical, how do we perceive the classical world as an emerging structure from the real, whatever it means, quantum world where that the universe is. Now, in order to make things precise, I have to tell first what means, or what do I mean by a classical system. For that, I'm not going to do anything fancy. I'm simply following, again, the inspiration by von Neumann and actually Birkhoff, that in the 40s, they actually were analyzing these questions, and the way to approach that was to consider what is the algebra of elementary propositions associated to a given system. Quantum, classical, doesn't matter. What is the notion of an elementary proposition? An elementary proposition is an observable that has only two outcomes, 0 and 1. That means that the spectrum of this operator consists only on 0 and 1, which is self-adjoint, and hence it is an orthogonal projector. So associated to any algebra of observables, M, to any von Neumann algebra of observables, there is the lattice of projections, which means operator. Remember that a von Neumann algebra consists of operators on some Hilbert space. So these are actually operators, P, which are self-adjoint and which are orthogonal projectors. There are two natural operations, or and in this algebra in this lattice of elementary propositions that corresponds essentially to the intersection of the corresponding ranges as operators in the Hilbert space where they are defined, and the subspace generated by the ranges of the two corresponding propositions or projectors. Then the notion of classicality is that a system is classical if and only if the lattice of elementary propositions is Boolean, exactly reflects the algebra, the Boole algebra of sets, right? So this is the notion of classical in contrast with what you will get for the general algebra of, the general lattice of propositions of a von Neumann algebra, which is far from being Boole, from being Boolean. It can be proved, not very hard, actually we did that a system described by a groupoid is classical in this sense, meaning by that the lattice of propositions of the von Neumann algebra of the groupoid is Boolean if and only if the groupoid, well, if and only if it is abelian, and this is equivalent to this algebra being, to the groupoid being totally disconnected and not related by any transitions, and such that the isotropic groups are abelian. It's always the algebra of essentially bounded functions. So this is a characterization of classical systems within. However, we have been using different names, and this has been the source of enormous with. Let me consider now that our groupoid, providing the kinematic and infinitesimal description, which is provided by a Lie algebra, which is related to the space of units. Then that, for instance, provided that we chose an auxiliary metric, groupoid, actually even more than that, if we can consider the classical counterpart to the groupoid, we can use the Legendre transform to move back and forth along the units. It's non-degenerate, for instance, right? Groupoid, together with a state, is going to provide us algebra together with a state, is what we call a non-commutative probability as before. The abelian von Neumann algebra of embedded in gamma, there is a canonical immersion algebra, the non-commutative von Neumann algebra in physical or the system we are describing. But this is not what we usually understand. This algebra with the Poisson algebra. Of course, this being an infinitesimal description of the construct, the groupoid, as we know that it can be done under the space, is what we will call, for instance, among people, even people here in the audience, the, so to speak, classic space, which is canonically associated to the solved partially by Jones studying subfactors. But here, what I'm known. Let me devote the last dynamics. So far, the picture is about the basic in classical. Now, what about dynamics? Of course, once we have our measure groupoid and the corresponding automorphisms of the algebra of observables, they will define a derivation of the algebra. Sometimes this derivation, say a Hamiltonian. And then we will recover, so to speak, in this system. But we can do something bad. Well, but what I mean by that is that if we have a state, one of these groups, Wampler and Takesaki in the 70s, and that was used essentially was one of. So this Tomita Takesaki theory says that, okay, in the particular representation of the state rho is separate antilinear isometry, call it J, and the representation, such that they satisfy some beautiful property. The other one is that this operator Neumann algebra. So this allows us to define a flow, this operator delta IT. Can create dynamics for Neumann algebra, so determine or define or particular or some this approach, which is quite very abstract so far, about specific systems, about concrete application idea in this talk, and is that all the variational principles play in the description of dynamics are a wonderful tool, ways that have been favored by nature at the time to describe what happens around ourselves. So whatever you want to call them, to the quantum level. And Schwinger's way of thinking was that, well, what I want to compute is here in some space-time, is that there is some nice space here. These hypersurfaces where, for instance, at this moment where we are living here, T1, there is a Hilbert space to stack all these objects, right? So there is going to be a state in this room. There were a time and a previous time, T0, time of what you would like to compute in order to obtain every possible from A T0 into B T. For reasons which are not relevant at this moment, the square Feynman did provide a direct formula to compute this, permeate all the discourse in theoretical physics. Each of these numbers, they have to satisfy some variational valued function. So L, this boldface L, is not a function. And this variation will be obtained by computing quantum variational principle by Schwinger, was that this, at the end, will at the boundaries, right? Of course, this following these years in order to elaborate all that one of the objectives of all this activity. In this principle to obtain his computation diagrams techniques that have become so popular, right? Let me say it again. So we don't know how to make sense really of all these things. To start trying to make sense of a dynamical description of quantum systems, right? So what are histories? Intervals into the groupoid satisfying his path starts at a unit, so at the initial time T0 map into a path in omega, right? Obvious source and target maps for gamma paths. This gamma path is going to be the target of the target maps. And provided that the source, when S is in between T0 and T1, which is the domain of the first gamma path, gamma path, W prime, composed with the Bayesian map is associative, there are units in a natural way, and gamma paths, because here there is a natural structure of this time interval, T0 and T1, and T0 is a small. There is a composition law which is associative, there are units, so they form a category. Actually, and this category can be groupoidified. I mean, you can consider theory, which is reversing the arrows, which are going to correspond to the inverses, the groupoid of. Actually, a better way of looking at that is thinking that his gamma, and then consider a homomorphism of groupoids, associating up an interval T0, T1 in R, right, on S, and fixing the first argument at T0. Convert, what we will have is that, provided that things now to associate to any universal history, this is a homomorphism of Lie algebroids. Technical description, remember, I need a state, and then we will use, in a natural way, a state there. Well, what I need is a positive, is something that come from the inside by any gamma path, a number, a complex number, which is an action-like function. What is an action-like function? Well, the sum of S at omega 1 plus S at omega 2, and S of omega times R. Actually, an additive function on the groupoid of histories is positive objects that were used by the three of them to the time of von Neumann to the next step, mental systems. Actually, the Lie algebroid, as I was saying before, the corresponding to the history omega from T0 to T1, the standard one that has to be done with care of this state, because now we have a state on what will be the dynamics. Well, the dynamics that you get is ALMA that we are working with is the groupoid of pairs of a space-time. You will get, when you compute that, is exactly the Schrödinger equation. So you recover Tomita Takesaki to these states, the Dirac DFS group in quantum systems described by as groupoids. This will be the subject for another talk here, and thanks for your attention.
Thank you very much, Alberto, for your nice lecture. So it's time for some questions.
I have a technical question regarding the definition of source fiber or are just paths in the manifold. So it starts on identity, but
yes,
then it moves.
They start at units and
Okay.
right,
So
and then you will have this, right? So you have space-time, x and t, and then the groupoid of pairs, say, there will be the unit, right? X0, T0, it agrees with the standard notion of paths, of histories in Feynman's. That what you are describing is a history of transitions, not terms. But you are taking track, you are taking down, taking into account all the physical information which is in the Yvette?
Do you implement the symmetries in this picture?
Oh, boy. And a group of transformations, so symmetries are implemented. If we have that the quantum system is described by a groupoid, a symmetry with some extra additional properties. And we like to call them, more on that, but this is the beginning of the idea.
Is the classical limit that you described, algebroid, with the sum on the fibers being the isotropies are abelian.
Yes.
I was just in this kind of picture.
So in this sense, very much like the case of a group and its Lie algebra, associated to a groupoid, to a Lie groupoid, is not losing the quantum setting of the quantum thing. An interesting question related to are going to be this linear functional normalized setting. This means on the dual of the Lie algebroid, which is a Poisson manifold, be a particular class of Gibbs states. The question is, how do you get one of these, Galabotti and others in the 80s, in the 90s, establishing the specific and constructing a limiting process in encapsulated form? Actually, we are working on that. This work has not been published yet, but.
Okay, another question.
So on obstructions to a Lie algebroid being integrable. So I wanted to ask if you interpret this as purely.
It's true. That's a very nice and interesting question, in the sense that there is not a simple groupoid based on that. Because you see, the last part of my talk was rather algebroid associated to that, right? This Lie algebroid, enough, topological, we will say, is going to introduce an equivalence relation. This means that there is going to be much going to collapse to provide following Fernand. So the fact that you have a Lie algebra which is not integrable in a subtle way with the groupoid of paths, which instances provided by the non-topological sigma models, right? In order to, the answer is that there are possibilities of unfolding the Lie algebra because they are not integrable, but something much larger.
Question during your talk. So there seems to be, at least naively, some tension between these.
A mental question. Microscopic reproducibility seems to be, just to make a long discussion short, if you want we can continue later, but along his career was not because used in a, so to say, fundamental way in fine structure constant and things like that, right? The groupoid, then causality, this is an old idea in the 80s, in the 70s, that started to study non-self-adjoint algebras. Very similar to the theory that lacking a physical motivation, this program has never really took off. I mean, here is, suppose you have the von Neumann algebra of a quantum system, so oriented things, and another one corresponding to past-oriented things. For instance, at a groupoid, we have to add past-oriented paths that move, combine causality with the groupoid structure, but specifically, in some cases, I can do that. It corresponds to moving forward in time, and another one that will correspond to moving mobilities. The contributions of both of them will have to be the institutes of physical quantities, right? General picture.
Thank you very much, Alberto. Can ask more questions.